The next situation for us to look at that you will often find when you're given a angular momentum problem would be when you have a single rotating object that somehow changes its rotational inertia, I, also called the moment of inertia, and that affects the angular speed of the object. So what we're going to do right now is I'm going to go over to a video from YouTube. I've put the link on Schoology involving a figure skater. You can start at about 45-50 seconds and see the whole video if you want to watch it, but I'll play it here for us real quick.
Is rotating with no net external torque acting on her. Angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
So, in that particular situation, we saw when the figure skater pulls her arms, legs, and torso inward closer to the axis of rotation, she started to spin a lot more quickly. That's simply using the law of conservation of angular momentum, where we say that the initial angular momentum of the figure skater should be equal to the final angular momentum of the figure skater as long as there are no external torques. So in her case, she had a large initial rotational inertia or moment of inertia because she tried to keep her mass as far from her axis of rotation as possible. Let's also note here that there is not some special formula for I when it comes to a figure skater because their shape is just too complicated. However, her I is still based on where her mass is located and how far away it is from the axis of rotation. We also saw that her initial rotational speed was somewhat low. But next, she started to pull her arms and legs inward. And as that mass got closer to the axis of rotation, which was aligned with the y-axis, her I significantly decreased because as that mass is closer to that axis, and you think about the fact that I is proportional to r squared, when that r value gets very small, the I value is also going to get very small. In order to conserve the angular momentum of the skater, her angular speed had to increase significantly to compensate for that reduction in I. In this case, we're assuming no outside torques, though one of the wrenches I suppose the AP test could throw at you is the fact that there is technically some outside torque here. And if you think about the rotation of the skater, where would there be a force that was causing a torque that would affect her rotation? Well, that occurs at the surface of the ice between the ice and the blade of the skate. There is a friction force. And what a skater is going to try and do is reduce that friction force and thereby reduce the amount of torque working against her rotation by keeping as little of her skate on the ice as possible. But in general, just like in linear motion situations where we ignore friction force, usually in cases like this, we'll ignore outside torques due to frictional forces. So those are the two situations that are most commonly seen on the AP test in terms of angular momentum. My final video is going to take a look at